Now, how about taking the ratios? Let's do in that way. Now, suppose we are looking at the first set where I'm keeping my B constant, which is not changing, but I'm changing my A from 0.1 to 0.4. Suppose that rate is rate 1. How do I write my rate 1? That's going to be K. What is the concentration of A in my rate 1? I'll just say K1. I mean, my rate constant is going to stay the same. Rate constant is not going to change in this case because we are using the same equation, right? And that's the reason why we call it a constant, right? So what is the concentration for the first set for A? Is 0.1. Do we know the value of A? No, not yet. How about my B? That's also 0.1. And I'm going to put B here. My rate 2, that's also going to be K, which is a rate constant, is not changing for a particular reaction. It's going to be constant. That's why we call it a constant. But now my B, my A has changed to 0.4. And my B is the same. If I take the ratio of my rate 1 over rate 2, see what happens. This will simply cancel out because the same value. But then this is not going to change. So A is not going to change, right? So I can cancel out my B, but not A. Now, do we know the value of rate 1? Yes, we know the value of rate 1. Do we know the value of rate 2? Yes, we know the value of rate 2. Let's put those values in that equation. I'm going to expand that so you can see what we have on the previous slide. So rate 1 is 1.0 10 to the power negative 3. Rate 2 is 2.0 10 to the power negative 3. That's going to be equals to K 0.100 raised to A over K 0.200. Am I right on that?
That's
No.
0.4.
Professor, wouldn't the case cancel out?
Yes, they will cancel out. So my K is going to cancel out. I can cancel out my exponent. That's fine. Now what I'm getting is 1 by 2 equals to 0.100 A 0.400 A. How can I solve this one now? Any guess?
Wouldn't it be equal to 1/4 to the A on the other side?
But then how do I take out that exponent A?
Log.
Absolutely, very good. So now I take log of 1 by 2, and I can say this is going to be A log 0.100, 0.400. And this is log to the base 10. Based on this, can you find me now A?
Divide by logarithm of 0.1 divided by 0.4.
Okay, can you find me that number? The final number for A, what that
2.
will be?
2.
Are you sure it's 2?
Yeah, it's log of 1 of half over log of 1/4.
Okay, so what that will be?
1/2 squared is equal to 1/4, so it's 2.
Are you guys getting that answer, all of you?
Negative 0.602.
Negative 0.602. Okay, so we are seeing interesting
I didn't
answers. Okay,
finish it. I just did log of
Mhm,
that. I
that's
didn't
fine.
finish it. Okay.
And just write down in the chat box so I know
doing the opposite on my head. So that was like, it's 0.5.
0.5. Mm-hmm.
Yeah.
That makes sense. All of you got 0.5, guys?
Yes, in the end.
Okay, so in the end, you guys got 0.5. And that makes sense because if you see here, you are increasing by 4 times, but the rate is jumping only by 2 times. So the order of reaction should be half over here. So now you can see a fractional order reaction. See, so it does not have to do with the coefficients that you write in the balanced equation. Now, let's see what we get when you try to find the order of reaction in your B. You're using the same method, right? Now, in this case, you are keeping your A constant, but you are changing your B. Again, I'm going to do the same thing. Rate 1 equals to K, which is constant, your concentration of A, which is 0.100. I'm not going to put the value of A at this moment because it's going to cancel out anyways. And my B is also 0.100, which is B. And rate 2, again K, I'm not changing the concentration of A, which is constant, but I'm changing concentration of B. If I take the ratios of this, I can simply cancel out this K, I can simply cancel out my rate constant, that's gone. And when you look at the rates, that's going to be 1.00 10 to the power -3. This is molar per minute. And the second one is 2.00 10 to the power -3. That's going to be 0.100 B, 2.150, that's B. Can you tell me what you get in this equation? What is B? Using the same method, using log.
One 1.71.
1.71, so I'll just keep it at 1.7. So you got 1.7 for B and you got 0.5 for A. Now let's write down the rate law. We call this as a rate law. So rate law gives you the rate, which is rate constant multiplied by the concentration of A. And what is the order in A? 0.5. Okay. And concentration of B, 1.7. Now you can see your order of reaction can be a fraction, right? Okay. Now, if you write overall order, that's going to be 0.5 plus 1.7. You are looking at overall order of 2.2. Now, this concept, the one which you have, the one which you just saw, this gives you fractional order reaction. So I'm just telling you that you can see those fractional order reactions as well. Now, there are, in general, when we do experimental chemistry, in general, we see 4 kind of orders. Most of the times, we do see fractional order. They are also widely prevalent, but then these are the most common. So we have first order reaction. We have second order reaction. We have third order reaction. and then we have zero order reaction. Now, what do we mean by first order reaction? That means if I write down the rate, that's going to be equals to the concentration of only one reactant. Only one reactant, and that's going to be order of 1. In your second order reactant, you can have one reactant raised to the power of 2. This is second order reaction. Or you can have another possibility where you have 2 reactants, each raised to the power of 1. That's going to be your second order reaction. You can have a third order reaction where you can have one reactant raised to the power of 3. You can have another possibility where you can have one reactant raised to the power of 2, second one raised to the power of 1. You can have another possibility where you can have A raised to 1 and B raised to 2. And you can have a third possibility where you can have B raised to 3. So now you see that the mechanism for all these cases in third order reaction is different. What does it tell you? In first, although B may be involved, but then it's not involved in the slowest step. The 3 molecules of A are coming together to give you an intermediate which may be reacting with B. But then that would be the slowest step. In another mechanism, you can see 2 molecules of A coming together with a B to give you the reaction. That would be the slowest step. In one case, you have 1 molecule of A and 2 molecules of B coming together to do the reaction. In the last case, you have 3 molecules of B coming together. A is not involved, although it may be in your reaction, but then it's not involved in the rate limiting step. That is the fast step where the product of your rate limiting step is reacting with B. All right. So the kinetics gives you the information about the mechanism. This is what I mentioned on the day 1 about this, right? About the kinetics. It gives you the information. And this is how you can deduce that information. Okay. Now, when we think about the first order reaction, as I mentioned, only A is involved. Only one reactant is involved, and that is raised to the power of 1. Now, is there any other possibility here? Absolutely. You can have A and B raised to the power of half and half. That would be first order reaction. But then those reactions are very rare reactions. We are not going to get into that, right? Just to let you know that those are possibilities which we see them, but not to that extent. Okay, now let me write down the first order reaction and how they will look like. So if you have C4H9Cl reacting with H2O, giving you C4H9OH, and one of the product is HCl as well. Now this one is a balanced equation, right? It's a hydrolysis of C4H9, which is your butyl chloride. Now this reaction is a first order reaction. Why is it a first order reaction? Because the concentration of water does not affect the reaction rate. So when I write down rate of reaction, that only depends on the concentration of my butyl chloride. I increase the concentration of butyl chloride by 1 time, I increase the rate by 1 time. I increase it by 2 times, I increase the rate by 2 times, because this is raised to the power of 1. This is an example of the first order reaction. So far, so good. Now, having said that, if I draw, let me take that equation. I'll copy that. Let me see if I can make it smaller. Okay. Now, can you tell me what is the way to convert an exponential plot into a linear plot? So the plot that you see on the left side is an exponential plot. How do I convert it into a linear plot? What operation should I do on that plot to get to a linear plot?
Derivative?
Derivative. See, if you take derivative at a different location, that's going to give you the slope. But I want to convert my entire plot into a straight line.
Maybe like the square root. I don't know.
So if you take a square root, that's still going to give you that number. Now, if you take a log of your reactant, what would happen then? In that case, suppose I take the log of concentration of this versus time. Now you're going to convert that into a straight line. Now, how does it play into what we are doing here? Let me go through that. Rate equals to K C4H9 Cl. But then the rate is also equals to the decomposition of C4H9Cl. That's what we saw before. That's the rate, right? So if this is equals to the rate log, if the rate is equals to that, can I equate these two together? Just like if A equals to B and A equals to C, can I say B equals to C? Definitely I can say that. So I can say dC4H9 Cl divided by dt equals to K and C4 H9Cl. Now, if I take the common terms on one side, let's see what happens. I will take the concentration of C4H9 on one side and I will take dt on another side. I'm separating these two variables, right? And let's see what happens with that. I got my concentration on one side. That's equals to K dt. Now, what we are looking at is the small changes in my reactant compared to the total reactant that I'm using. See, we are looking at the ratios now. How much change was there compared to the total amount of the reactant? And what we are comparing it to? We are comparing it to the time. So what should I do in that case? I should be using integration. So I should be integrating this equation like this. And we can only integrate, keep in mind, we can only integrate the variables. We cannot integrate the constant. That's why I kept K out of the integration. So this is going to integrate to log, which is a natural log of C4H9Cl. That's going to be equals to K, and dt, integration of dt will equate to t, and you also need to add a constant. See, this is now with a logarithmic function. We got that. Now, this equation is similar to y equals to mx plus c, the equation of a straight line. This is your dependent variable, which is the concentration of your reactant. This is your independent variable, which is time, and the slope gives you the rate constant. C is the intercept on y-axis. This is exactly what I drew in the previous case. So now if you take natural log C4H9Cl and you plot it versus time, you get a straight line. Slope of this line equals to m. Intercept is your C, right? And when you look at this equation, we have a negative sign over here. That means your slope should be negative. because you can take this negative sign on this side by multiplying this entire equation by -1. So now you are looking at a slope which is negative, and you can see the line is in opposite direction. So it tells you that with increasing time, which is with increasing your dependent variable, you are decreasing the concentration. Now, for the practical point of view, you can use the plot to determine the rate constant, and you can also find, I would say, at a particular point, you can also find the instantaneous rates. Now, let me give you one more equation. Suppose if I were dealing with a finite integrals. Now we can solve it for the finite integrals as well. Okay, but then there is no space on the right side. Okay, so we can solve it for the finite integrals as well, just by putting our initial concentration here and the final concentration, initial time, which is 0, and the final time t. How will that equation look like? So let me write down the final version. If you guys want how I got there, you can meet me in the office hours. I'll be happy to show you how we got there, right? But then the equation that you need to know is natural log a over a minus x. That's equals to kt. What is a? Is your initial concentration of reactant. A minus x is final concentration of reactant, which is left at that time. T tells you the time, and K tells you the rate constant. Now let's solve one problem on that. Just give me a second. Let me copy paste that problem because it's a good one actually. So you are given the rate constant of first order decomposition of cyclobutane. You are given temperature, and you are given the value of rate constant. It's a first order reaction that's also been given to you. And it says, how long will it take for 80% of sample to decompose? Okay, so in this case, first I'm going to write down my equation. Natural log a over a minus x. K1T. Now I've written here 1, that means I'm indicating that's a first order reaction. That's what I'm indicating. Now, can you find me what is A from this data? And this is your reaction. And I can also tell you
Would
that
it
the
be
rate-
9.2 times like 10 to the negative 3?
Okay, let's see that one. Now, A is supposed to be the initial concentration. A minus X is supposed to be the concentration which is left in your reaction, right, at time T. So first of all, let's see what is given to us. 80% of the sample has decomposed, right? So if my initial concentration was 100%, how much is left? See, 80% is decomposed. How much is left? That's going to be 100%.
20%?
Exactly. So only 20% is left. So I can use exactly these same numbers in the equation. Am I given K? Yes, I'm given K. What I need to find is how long will it take? I need to find time. So I can write ln, which is natural log of 100 divided by 20. That's going to be K1. And we are given the value of K1, which is 9.2 10 to the power negative 3 per second multiplied by, we need to find time. Can you find me this value?
Professor,
Mhm.
just out of curiosity, how does percentage over here mean concentration or initial or final concentration?
We can use it as it is because here we are giving the sample. So suppose if you are given 1 molar, that may be 100%. And if you are looking at the remaining 20% of the sample, which is remaining, that's going to be 0.2. So if you are taking the ratio of 1 to 0.2 is same as 100 to 20. So I can use as it is. So I can, yes, so I can use the ratios in that form because we are using ratios.
Professor, if it's one sample, wouldn't all of it be 1 molar?
I'm sorry, what's that?
If it's one sample, wouldn't it all be 1 molar? Wouldn't it all be the same concentration?
No, it's not going to be because 80% is already decomposed. So it has to be 0.2.
Oh.
If you start with 1 molar, then you are left with 0.2. Yeah.
I
Mhm.
understand. Okay. Perfect.
Okay. So guys, what is the answer in this case? $175 seconds. Okay. Looks like you got that answer correct. How many of you got 175 seconds?
I got 1.75 to the -4 times 10 to the -4.
No, it has to be positive number. I mean, it has to be I don't think it's going to be 1.75 seconds. You need to take a natural log, guys. Make sure of that.
Professor, the reason why he got 1.75 times 10 to the fifth may be because he didn't like put the parentheses between like 10 times to the -3rd. So like it did it after it divided by 9.2.
That may be the reason. Yeah. So if you get 0.1749, but then it has to have an exponent 10 to the power 3. So that's going to be 175. Okay. So
Professor,
almost
175 seconds or 1.75?
175 seconds. That's the
Okay.
answer.
Okay.
Now imagine, I mean, how many of you heard, many times, like many times we see this in the news that whenever there is, like a nuclear threat, right? People will start to accumulate iodine from the stores. Have you seen that? Have you heard about that?
No, Professor.
Yeah, I mean, it's like, and it still happens, whenever it's in the news that there is a nuclear threat in some area, people will start to accumulate iodine salt or iodine in pure form. They will start to accumulate that just to make sure that they are not affected by radiation. So why do they do that? Any idea about that? Any idea why why iodine is important? Let me give you that information. Now, generally, whenever suppose there's a nuclear explosion in some areas, everything in that area, around that area, will be contaminated by radiation, right? The food that you will get will be contaminated by radiation, and the food will contain iodine that will also be contaminated, and that's going to be a radioactive iodine. So what's going to happen? You take that food, that iodine will get into the thyroid gland, and that iodine can damage the thyroid gland. The radioactive iodine can damage the thyroid gland, and thyroid gland is inherently connected with several growth hormones and is involved in a lot of metabolic activities in our body. So what happens within the matter of days and probably months, people will be diagnosed with a thyroid cancer, right? So it gets really, really important that at that time, people should be ingesting the normal iodine. Why normal iodine? Because the normal iodine, if you take higher concentration of normal iodine, the radioactive iodine, which you get through the food, will get inside the body. That's fact. But then it will not be accumulated in the thyroid gland because the normal iodine concentration is so high that it will not let the radioactive iodine get inside the thyroid gland. It will go there, but it will not be accumulated. The regular iodine is going to replace it, right? This radioactive iodine takes around 7 days to decompose, right? So after 7 days, that food which has radioactive iodine will be fine. But then for 1 week, people need to worry about that, right? Now, many times people will misunderstand the role of iodine, and they will collect the iodine in such a huge amount. They think that is stopping the radiation. No, iodine doesn't do that. I mean, so if people tend to think that if they apply iodine on their body and somehow they can escape radiation, no, it's not going to work like that. It's a chemistry, equilibrium. We're going to discuss that. But then just to let you know. Now, here you are given radioactive iodine, right? So it undergoes decomposition. It gives out a beta electron. Okay. And it's a first order decay. That means it's a first order reaction. When that happens, the rate constant is 0.138, and see D minus 1. That means we are expressing our time in terms of days. We can do that. If you're doing nuclear chemistry, you will see the time expressed in days, in the rate constant, sometimes in years, sometimes in minutes, sometimes in seconds. We do that all the time in nuclear chemistry. Okay, but see, this one is in days. Now, what it's asking is, how many days will it take for 90% iodine to decompose in 0.5 molar solution? Now, how do I start with? Can I use the same equation? See, here I'm given concentration, and that is 0.5 molar. Now, I can take 100% as 0.5 and 90%, which is the remaining like 10% as 0.05. I can do that. But instead of doing that, I can take the simple percentage. So I can take A as 100% and A minus X as 10%. It is same thing as having 0.500 molar as 100% and 0.0500 molar as 10% remaining. The ratio is going to be still the same. Okay, are we given K? Answer is yes. What is that? 0.138 days minus 1. Can you find me how many days will it take? Can you find me T now?
I got 16.7.
Got 16.7. How many of you got that?
So Professor, what you're doing here is using the percentage given along with
Yeah.
the initial molar in order to find what the final concentration would be.
No, we are trying to find the time. How
No,
long will it take
No,
to
no,
get to
I'm
10%?
saying the 0.05, the way you got there was using the percentage.
Yes, absolutely. Yeah.
Professor, I have a question.
Mm-hmm.
What do you do if like if it decomposes completely? How can you calculate it?
No, it will never decompose completely. Never, it
Okay.
will never happen. There is a reason, because this is an exponential plot. So it will tend to get to zero, but it will never get to zero. So whenever we have an exponential plot, it will go like this, but then it will never become zero. It cannot happen. So this one would be quite similar to, for example, if you are trying to move from point A to point B, right? I'm just giving you an example. And if you start from point A, your every step should be half of the first step. Think about that. So if I go for the first step over here, well, I took a first step. My second step should be the half of the first step. So I will take my second step, my third step, my fourth step, but I will never reach B, because every step is a half of that. So think about an exponential plot like that, right? So it will never get to zero. In fact, in any nuclear reaction, in any first order reaction, you will never get to zero. So in this problem, if you are getting the answer 16 point, how much did you guys get? 16.6 or 16.7 days? That would be correct. Okay, now using the same example, can you tell me how long will it take to reach 50% of what you started with? So this time, what I want you guys to do is use molar concentration. Use molar and find me how long will it take to reach 50%. So A is given to you. In this case,
5 days.
let's see, let us see. A minus X, you are looking at 50%. What is 50% of 0.5?
0.25.
Okay, so this is 100%, 0.250 molar. That's going to be 50%. Okay, can you find me the time now in this case? Using the equation that we did. So I'm going to rewrite that equation. Natural log A over A minus X equals to K1T. And keep the rate constant same. Do not change the rate constant. You use the same rate constant. Can you find me T in this case? All of you got 5 days?
Yes.
Okay.
Or is it 50?
Okay. So 5.02. So you got 5.02 days. Now, can you find me how long will it take to go from 0.250 to half of that? See, every time now you're going to half of that. So now in your new case, you start from 0.250, which is remaining in your solution, and you go half of that, which is now 0.125 molar, which is remaining. So this now becomes your 100% for step number 2, and this becomes your 50%. Can you find me T in this case? Again, 5.02. Absolutely. See, that is the beauty of first order reaction. In first order reaction, the half-life time, that means the time taken to reach the half concentration, does not change. That stays the same. So we write it as T half. So this is the sign of T half. Now, easiest way to find the half-life time instead of doing this calculation is quite simple. Let me derive that equation. Minus x equals to k t. If A is 100%, A minus x is 50%, that is equals to K1 T. Now, since we are dealing with a half-life, I'm going to write it as T half. Now, log of 100 divided by 50 is log of 2, and log of 2, natural log of 2 is 0.693. So 0.693, and you can go for one more, 0.6931 equals to K1 T half. So I can find half-life time without going through that trouble of putting those values using this equation if I know my rate constant. It is interesting that for a first order reaction, the rate constant is the one which determines the half-life. So half-life is always constant because rate constant is constant, right? So let me show you that plot.
And this only works if this is first order.
Yes, that's going to be only for the first order reaction. And every time, so let me show you this example. Here in this case, you are seeing the decomposition of methyl isocyanate. Now, have you guys heard about this gas, methyl isocyanate? We call it MIC.
No.
This gas was released back in 1980s in India. And if I remember correctly, almost 10,000 people died instantly on the street because of this gas leak, right? And after that, there were several people diagnosed with a variety of, like genetic disorders. So this gas is very, very dangerous gas, right? Okay. Now, this can decompose. This gas can decompose, right? And as you can see, if my initial concentration is, say, for example, 150 torr, since it's a gas, we measure the concentration in terms of pressure of that gas. So if it is 150, getting half to the half of that, right? Getting to half of that, 75, see how long it takes. So from 0 to 10,000 seconds. That's the half-life time, right? Okay, going from 75 to 37.5, again half, look at how long it takes. It's the same thing?
No.
It is the same
Yeah.
thing. It's the same thing.
Is it 10 to
Yeah.
30, not 20,000 seconds?
I'm sorry, what's that?
Isn't 10,000 to 30,000, 20,000 seconds?
It is a little bit more than 10,000. I think this one is almost 12,000, something on that lines. And the next one is also 12,000. So this one is 12,000. This one is also approximately 12,000. So
Oh,
you are
okay.
looking at
I was
difference.
looking at
Yeah.
the wrong lines. I'm sorry. I was
So even this one
looking
will
at
also be
the wrong lines.
12,000.
Right. Perfect.
So you can see the half-life does not change in this case, right? Okay. Now let's go for our second order reaction. Now, before I do that, let me give you an example of carbon dating. Have you guys heard about carbon dating before?
Yeah.
Do you know what carbon dating is?
Yes. Using the half-life of carbon to determine how old something is.
Exactly. So that actually tells you how old a sample is. So for example, if you take isotope of carbon, which is 6C14, that can decompose into nitrogen 14 plus a beta particle. Now, beta particle is an electron which is emitted by the nucleus. It's a beta particle, right? Now, this process takes 5,700 years. Now, why it is important? Because when you look at the natural abundance of carbon-14, it is roughly, if I believe correctly, it is 1 part per trillion, 1 ppt, right? But then if you take a sample of carbon from nature, that amount is always going to be there. So out of 100% of your carbon sample that you are getting, 99.9% is carbon-12. You don't need to worry about that. But then tiny portion is 6C14, which is an isotope which undergoes decomposition every 5,700 years. So that is the half-life, T half of your carbon-14. Now, how does it help us to determine how old the sample is? Well, suppose we have a living organism. This living organism is taking glucose because we take glucose all the time to survive, right? And that glucose in variety form, you can take it, but then that has carbon. In fact, we are carbon-based life form. So we are constantly taking carbon inside and we are giving out carbon in form of CO2, right? So there is an equilibrium of how much carbon-14 I'm taking and how much is getting out. So there is always that number which is constant within us all the time. Now, suppose if this person dies, now this person is not taking glucose from outside. So whatever carbon is there is still in this person, right? Now, at that moment, this person dies, the amount of carbon-14 is trapped within this person. So what happens? Carbon-14 will start to decompose. Now, suppose after 15,000 years, or probably after like 20,000 years, when I check this person, when I get the sample from this person, and I see how much carbon-14 is remaining, I can find the age of this person quite easily. Let me solve one problem on that. And by the way, how do we know how much C14 is remaining? We can detect how many beta particles are being emitted. It can be done, right? So suppose the fresh biological sample is giving out 15 disintegrations per minute. That's the fresh sample. So if I take the sample from a living person, it is going to give me 15 beta particles every minute. 15 beta particles are coming out from human body every minute. Now, if the old sample, which I'm getting, that is giving me 8 disintegrations per minute, or let's put it as 5 disintegrations per minute. What is the age of sample? Was to K1 into T. I need to find T. I already have A. I already have A minus X. This one is your A minus X, which is the amount of disintegration happening at that time, which is the remaining amount of carbon-14. This is basically A. So what piece of information is missing? K is missing. How do I find K? Well, K depends on the half-life. Are we given the half-life? Yes. That's going to be 0.6931 divided by 5700 years. Can you find me K over here?
Professor, is that an equation for half-life? That's what we.
Yeah. We are using that equation. Yeah. Are you guys getting 1.21? Let me see what we have on a chat. That's right. 1.22. Okay, that's fine. 10 to the power -4. And make sure you write down the units properly. It's per year. Now, we found K1. Can we find T? Now, here, A is 15 disintegrations per minute divided by A minus X, which is the remaining amount, is giving me 5 disintegrations per minute. And I just found the value of K. And I need to find, this is per year, and I need to find T. Can you find me how old is the sample?
Oh, it's the same.
I'm sorry, what's that?
I got the same. I got the 1.22 times 10 to the -4.
I think that's going to be different.
I'm sorry, I got 9,005.
9,005.
0.02.
See, I'm getting, I'm getting a different answer.
Professor, it depends on which round, like how rounded you use the 1.21. Because if I use the
Okay.
unrounded answer, I get like 9,036 years. If I use the 1.21, I get 9,079 years.
9,079. Okay, so
It's around
not a,
9,000.
yeah, so I mean, we can take it as 9,079 or 9,036. Okay. So we take 9,036 years. This is how we do the carbon dating, right? So that being said, let's go to the next part, which is the second order reaction. Now, what do we mean by second order reaction? That's where we have two compounds involved, or probably one compound with the order of 2, right? With an exponent of 2 involved, right? So I'm going to write down that equation, and then let's see if in that case, does the half-life depend on the concentration? So suppose I have an equation giving me the product. In this equation, I can write down rate equals to minus dA by dt. That can be equals to K1. In this case, I'm going to rewrite it as K2. That means I'm referring to the second order rate constant. That's going to be like that. Okay. Now, interesting thing is we can solve this using integration the way we did it earlier. But as I said, that's not going to be what I'm expecting from you in this class. So I'm going to give you the final version once we do that. We can do the integration for this one, but then the final version will be 1 over A, which is the concentration at the time t. That's going to be equals to K T plus 1 over A 0. This is the initial concentration. This is the equation for the second order reaction. Now, we can get there, as I said, using the method of integration, but then this is not what I expect from you. But you should know this equation, how to use that. You should know how to use that one. Okay, now let's try to find the half-life the way we did it in the previous example. So,
Professor, what's the 0 at the A? I'm sorry.
okay, so that means we are dealing with the initial concentration. A0 is your initial
Got it.
concentration. A is the final concentration. This is the rate constant. And this is the time. Now, if I want to find the half-life for the for the second order reaction, let's see what is happening. Now, in this case, suppose A equals to A0 by 2. Let's see what happens if I incorporate that value in this equation. So 1 over A equals to K2 T half. I will just say first T, and then I'm going to put that value. Since A is A0 by 2 for a second order reaction, I can say this is A0 by 2 equals to K2T plus 1 over A0. Now we are dealing with a half-life. That's going to be T half. Can I rearrange this equation as this, giving you K2T half plus 1 over A0? I can do that. And then finally, I can say 1 over A0 equals to K2 T half. See, this time, my T half does depend on my initial concentration. So higher the initial concentration, lower is the half-life time. It does depend on the initial concentration, right? Unlike the first order reaction, in second order reaction, it does depend on that. Now, We will complete this chapter, start the next chapter next Tuesday. And what I want you guys to do for homework, very, very carefully, listen to me carefully about this one. Give me a second. So the next chapter is going to be on chemical equilibrium, which is your chapter number 15, right? So what I want you to do, go through the slides, go through the videos, which is saying chemical equilibrium 1 and chemical equilibrium 2. So you will also be doing video 5 that is due before June 20th. So complete that and also go through the videos that I've given to you in the course video. Go through that. What we will do, we will start to solve the problems directly from these videos and from the slides. So keep in mind, you should be doing those videos before coming to the class. We want to spend as much time as possible on solving the problems. So next week, complete them, right? So let me put it here.